Hi, my name is Hugh Mckee. I'm a developer advocate for Lightbend, and my talk today is about how to build megaservices, or really how to build higher throughput microservices. What I want to do is kind of jump right into a demo to get things started. And this demo, I've been working on this for the last few months. I wanted to have some kind of a demo where I could push the system, push like a microservice application to its limits, basically, based on whatever platform I'm running on and all the different components that the microservice system is using. So I'm going to go into this live demo, which is IoT based, Internet of Things based, and it's been a fun application. That the fun part of it is that the user interface, it's a web-based user interface for the demo app, is map-based. So what you can do with this demo application is browse around a map. So let's just go ahead and jump in and we'll take a look at the UI. So I'm just running at a web page here. The information that's shown on the screen is coming from the backend microservices, and the idea with this web application is that you can use this user interface to position simulated IoT devices in different geographic locations around the world. So the map behaves very much like maps that we're familiar with, like Google Maps and so on. And one of the things you can see here is that there's markers distributed in different locations around the world. And these markers indicate where I've pre-populated some devices. And the colors also give me, some indication of the state of the devices. So green obviously usually means it's good. Red means something's bad, and then yellow means caution. And in this case, what it means is that there are devices in these different locations, and the devices have a simple state. The state can either be that the device is happy, it's green, or it's sad, it's red. And a yellow would indicate that there's a mix between some devices in that location are happy and some are sad. So to give you an idea of some of the information that the app provides, if I mouse over different geographic regions, it's giving me a count of the devices in this big region. So I'm zoomed all the way out as far as I can go with this map. And for example, in the European area here, there's 24,000, almost 25,000 devices. In the London area, there's almost 19,000 devices. And also it shows me that there's around 65,000 or 16,000 that are happy and around 2,648 that are sad. So this information is coming from the app. What's being fed. What this UI is doing is just some JavaScript that I wrote that is included in a demo app that I'll give you the links to at the end of the talk. That is about every 200 milliseconds is querying the back-end services. What's the current state of the devices around the world. So it's doing a quick query, and all this information is coming back from this query. And it's showing different things. Now, just a quick tour of the interface. Up in the top left, there's some information. There's an indication of zoom, and what that is as you zoom in or out on the map, there's a zoom level. So it goes from zoom 16, which is zoomed furthest away from the Earth, to down to zoom 1, which is the closest that this UI will go to the Earth. When I move my mouse around, it shows the latitude and longitude of where my mouse is located. And then there's another one, it's called device density. And what this means is that, in theory, that each region, each of these rectangular regions that in this grid that's superimposed over the map, each of these regions could hold up to a billion devices. And this is just the way I set up this app, for the way it works. In theory, I could potentially create a billion devices in this region if the back-end system can handle it, which is kind of one of the big goals of this demo app. It was to explore the limits of technology. And then on the bottom, on the bottom left, there's a devices in view, and as I'm zooming around the map, it'll just keep a count of the devices I can see at whatever location I'm looking at the map. And then on the right, there's devices worldwide. So right now there's around 200,000 devices that I pre-populated around the world here. And then there's counters on the happy and sad states or status of those devices. And then in the middle, there's a little kind of just an activity indicator graph. As I'm performing operations like creating devices or changing the state of devices or deleting devices, that kind of activity, it will be shown in this graph in the middle here. So let me zoom into an area. I'm going to zoom into the London area. So as I'm zooming in, you can see the devices in view now has changed. Now we're looking at 43,000 in a split between London, Paris, and I think it's Berlin or Hamburg. But I'm going to zoom into London. And as I'm getting closer, what you start to see is those markers give way to showing regions of where devices are distributed. And so here what I'm showing is that I'm zoomed down to a level where the device density is 1,024 per region. So as I move my mouse around, it's giving me counts of the devices in these different regions. And it's also showing me the status. So, a lot of the devices are happy, they're green, but some of the devices are showing up as unhappy. They're red. So this is just me playing around with this user interface. So the idea with this is that you can create devices and you can manipulate the state of devices. So I'm going to zoom into the lowest level, as close as I can get to the Earth. And the device density goes to 1. So what I can do is, now what's shown up in the top right is a little menu, kind of a help information. And it's showing that I can set a rate. And this is when I make device operation changes, they go into the services, the backend services, at a set rate. They won't exceed that rate. And so I don't like because I can do operations, as I'll show in a bit, where I'm changing hundreds or thousands of devices, or creating them, they're deleting them, changing their state, and so on in like a single click. And I want those things to flow into the backend services at a specific rate. And then there's also little indicators: C for create, D for delete, H for happy, and S for sad. And what that means is that if I type C, for example, the C character, then when I move my mouse around, it highlights the region where I could create a device. And since the device density is 1, it will create 1 device. So if I click it and it goes well, we should see 1 device show up here in hopefully in a moment. There we go. But big deal, right? I've created 1 device. The fun begins is when you zoom out. And as you zoom out, it zooms out, or the device density increases by a factor of 4. So if I zoom all the way in, the device density is 1. If I zoom out 1 level, it's 4. Another level, it's 16. Another level, 64, 256. So now, if I were to do a create, what this will do is send in a request to create 256 devices in this geographic region. You're kind of evenly distributed around this grid. So that's what I'm going to do. I'm going to click this. I'm going to zoom in a little bit. And what we should see then is the backend service start to create those devices. And I'm going to go into how this application works in a bit, because it's kind of interesting what's actually happening. And the data that we're seeing is also interesting. So now each of these little grid regions has 16 devices. But 256, again, kind of big deal, right? So say I'm zoomed out to, I'm going to zoom out to 1,024, do a create, and I'm going to decrease the rate a little bit just to show you something. When I do that, I'm going to decrease it from 1,000 to 500 per second. And you can see that if you look at the top corner of the highlighted region, it's showing that it's saying 2 seconds. And what that is an estimate of how long it will take all the device create requests to be submitted. So if I click this, and I'll zoom in again, we should see these devices get created. And you can see the counts going up. So there you go. So I just created 1,024 devices. So this is kind of like when, these are IoT devices simulated getting created, but in a way this is also simulating things like you had 1,000 customers hit the buy button in, over the course of 2 seconds. And the back-end system had to be able to handle that. So this is what this app can do. Then if I type an S and say to make some of these devices sad, and I click it, then another request goes in. There's a bit of a delay while it's processing it, and then what we should start to see is those devices, their state changes to sad. So hopefully that'll happen here in a moment. There we go. It's starting to happen, and then we should see that this all gets processed, and 100. There we go. It's done. So what's happening in the backend services and what's going on here? So let me go back to the presentation. So first, the term megaservice. I'm just kind of playing with the term service. We've been talking about microservices for the last 5-6 years or more. They've gotten really popular, of course, in the last few years. Many of you are building microservice systems now. It's becoming the norm for many developers these days. But I wanted to kind of play with the prefix, the service prefix. So instead of microservice implies that it's smaller than a monolith, it's less complex, it's more focused on a particular task than the traditional monolithic type of way of building applications. Here, the prefix implies performance characteristics. So mega is really kind of pushing the boundaries where when I'm saying a megaservice is a microservice is capable of processing millions of logical operations per second. And I'll define what a logical operation is in a second. I'm sure you can kind of, what that is. But so the idea is the context of the prefix indicates the expected performance. So just playing with that a little bit, you can think about services now as, do you have to build a Deca services that only has to handle, say, tens of operations per second, or a hecta service, hundreds of operations per second, or a kilo service, thousands of operations per second? Or, are you really starting to get up into the big leagues, building services that have to handle, significant traffic? I think many of you are in the area of hecto and kilo services. And probably many of you are in the kilo service area. But probably a lot of us, you build applications that fall comfortably in the hecto service area, where we just have to be able to handle hundreds of operations per second at our peak loads, say, not necessarily 24/7, but the thing is, your service doesn't matter how well it handles the off-peak loads, but your service needs to behave well when it's handling its peak load as well, whatever your peak loads are. So I think many services these days are starting to fall into the kilo service area. And I think that that's just going to grow. But here we're talking about maybe thousands of logical operations per second, or tens of thousands, or maybe hundreds of thousands. And now you're really getting into, again, the big leagues, so, the high volume applications. So with a logical operation, it is fairly straightforward. It's like with an IoT type of an application. So an operation that creates a device. The backend system has to be told, okay, here's a new device at this location. Say maybe a customer hooks up a device in their home, and there's a phone app that the customer can use. Well, there's a backend service that's supporting that phone app, and that's the real interesting architectural behavior of let's say, an IoT type of an application. In a more traditional type of sense, though, say the shopping cart. A logical operation would be the user adds an item to the cart. That's going to trigger some back-end activity, right? We know that. And changing the item. So building up the shopping cart and then ultimately hitting the buy button. Each one of those different operations is considered to be a logical operation. And each logical operation on the back end can trigger a lot of things to happen. And the big things are things like you're invoking various service operations. So a service operation may involve some computation, but it also almost always involves some kind of database operations. And it's really the database operations that take a good chunk of the time for the overall logical operation time, execution time. Also, some services will talk to other services. So another, some kind of a service operation would be inter-service communication, collaboration, those types of things. But one thing I've been running into, I've been working on building applications, enterprise applications for decades. And one of the biggest limiting factors was that kind of determined how fast the application could go was how fast could we push the database. Now, of course, we have to be able to scale the application as well, but often that was much easier to scale than scaling the database. And now with microservice systems, we also have to, if you're building systems where the services are talking to each other, you have that interdependency between, one service A invokes some operation in service B, and that operation takes some time. So service A is waiting for that operation to complete. So these are the things that happen inside of a logical operation. So with this demo application, there's two microservices. There's a where on Earth, the application is called Where on Earth in WOE. So there's a simulator microservice, the one on the left, and then there's a twin microservice. So the simulator microservice is simulating the outside world. It's pretending like it's IoT devices. And then the twin service is, the reason I call it a twin is some of the folks at Tesla are doing some really cool stuff with one of the IoT application in Tesla. And they kind of came up with a term that they've been using that I really like called digital twins. And what that means is that for every physical device that's out there in the real world, there's a digital twin device in the background. So that's why I call this other service twin. So what happens is that when I send in requests, say to, I do a click and say, all right, create 1,000 devices. That HTTP request goes into the SIM service. The SIM service gets that single request, and then through using Akka actors and so on, I really don't have the time to get into the details of it, but it is pretty cool. One request comes into the SIM service, but then 1,024 requests come out of the SIM service and get sent over to the twin service. Because I want to load up the twin service as if 1,024 devices came online within whatever rate, time frame that I've set. So say the time frame is 2 seconds, or I'm sorry, 500 per second. So it's going to take 2 seconds to create 1,024 devices. Then that's what's going in. So the idea is that the SIM service is going to be sending over 1,024 telemetry requests, and I'm using gRPC in this. And I can also use HTTP. It's a configurable thing. I've been testing with both, but been trying gRPC. So basically, the SIM service sends over 1,024 telemetry messages, which the message contents say, create this device at this region on the map and make it state happy. So that's what's going on with these services. So these services can scale. They can go up where, because they can scale up, they can scale down. They are both running in Akka clusters. So not really going to get into too much detail on Akka, but Akka is basically an actor system that can run in a cluster. So a cluster is this natural environment. So these microservices are written using Akka microservice technology. But the idea is that these services can scale up. So as the load goes up, they can scale up. As the load goes down, they can scale back. And there's a resiliency as well. And, if say one of the nodes in the cluster goes down for some reason, then it can get replaced. And where I'm running right now, the demo that I'm running right now is running in Amazon, in Amazon Elastic Kubernetes Service, EKS. And I'm using so Kubernetes in Amazon, and I'm also using some Amazon serverless databases, key spaces for Cassandra API, and then Aurora RDS for Postgres API. So I'm using a couple of different databases in these microservices. And of course, I'm using Akka to build these things. So, and the microservices are built using CQRS, or Command Query Responsibility Segregation. It's not CRUD. And the reason for this is that there's the whole reason for segregation, splitting things into what the segregation is, splitting the write side from the read side. And I'll show you that right here, is that you're trying to optimize the performance. So if you're not familiar with CQRS, I'm going to give you a quick introduction here. I'm not going to go into a ton of detail on it, but it is a very interesting way to handle persistence. So the idea is that starting in the right, say client requests are coming in, whatever the client might be, into some kind of a service. And there's basically two types of requests that this service handles. There's commands, as they're called, which are requests to perform some kind of operation, some kind of a state-changing operation. We're going to make some changes to data. And then there's the other type of request is queries. I want to just read some data. So when a command comes in, it goes into it in what's called the write side. And the write side, what's happening here is that a command comes in, which is a request to do something that hasn't happened yet. And then the request is, the service looks at it, it validates it. If everything's fine, and then it's going to process it, what then happens is that it emits an event, or maybe one or more events. And then those events are stored in what's called an event store. The idea here is that there's no updates, there's no deletes, there's only inserts. So this is a very simple structure. The database operations are very simple, and they're very relatively fast compared to, say, doing some kind of a transactional CRUD-like operation where you're maybe updating some rows, inserting some rows, maybe even deleting some rows in the course of say a logical operation, to perform some kind of a function of that results in performing a database operation. Here, it's just inserts, and then what happens then is that the data in the event store isn't very queryable, though. The types of queries you can do against this event store is very limited. So that's by design, though, because the queries happen on what's called the read side. So as events are being accumulated in the event store, as quickly as possible in the back end, those events are being processed and put into views, basically, queryable views. So this is the segregation part, the split between the write side and the read side. Because when a client makes a request and it gets processed through and it emits an event gets committed, that transaction is done. And now we can go back to the user and say, yep, we performed the operation you asked us to do. We haven't necessarily done the operation on the read side yet, moving or processing these new events into the read side. That's not part of the same transaction, typically. So this is good and bad, because the good thing is it helps to optimize the performance. The bad thing is that it comes at a cost of eventual consistency, where the consistency of what is the state of the data in the write side and what is the state of the data in the read side is eventually consistent. Eventually, all the events will get processed into the read side. This is a little hard at first for people that are new to this to get used to this pattern, but it is quite powerful. And once you do get used to it, as we typically do, at first it looks like, oh, I really can't use this, but the more you use it, the more you understand it. You start to learn how to live with it. That you can really start to take advantage of it. So then the other thing, though, is that it frees up the whole kind of balancing act that you have to do between, basically, the typical balancing act is you're optimizing for writes at the cost of reads. You're optimized for reads at the cost of writes. And, the big thing, like with a relational database, is you add indexes to make your reads faster, but your writes are slower. So you remove indexes, so your writes are faster, but then your reads might be slower. So you're playing this balancing game. Here, it's trying to split that apart, right? That the data structures in the read side are really optimized and not necessarily normalized for, in the traditional sense, but they're optimized for the different kinds of queries that this service needs to support. So this is CQRS. It's a very interesting pattern and ways for handling persistence. So as I said, the motivation for CQRS, and there's multiple motivations. One of the big ones, though, is increased throughput. You just want the things to run faster, and you're running into, say, limitations where they stateless, say a traditional stateless CRUD application that we all know and have probably built many, many times, and it's a great pattern. I'm saying anything's wrong with stateless CRUD, but when you have high volume applications, you might run into that ceiling where the database simply can't go any faster because it's handling all of the concurrency mechanisms and locking and things like that. And at some point, the database just can't go any faster. This gives you kind of a bumps that ceiling up typically. This is one of the reasons for CQRS, because it's reducing contention. The other thing I think is really big, though, is that it's kind of a freedom in the way you do your data models. Because now your data model on the right side is optimized for writes. And that's it, really optimized for writes. And the only operation you're really doing is insert. On the read side, however, it's optimized for the queries. So it could be that you could have multiple databases for the different kinds of queries. For example, a lot of queries are best done in a relational database, but maybe some queries are better done in, say, Elasticsearch, document types of databases, and you want some kind of Google-like search capability off of the documents. That's possible here with CQRS. It's relatively easy to implement. And Akka really works out well with CQRS as well, because there's this concept of state where in Akka, it's the actor model, and actors are basically objects that have a strict way that you communicate with them by only sending them messages. So it's easy to, it was a natural thing for us to use Akka in CQRS because the state of a thing, like the state of the order or the state of an IoT device, can be hot in memory while it's in use. And whereas, say, with a stateless system, by design, I think of it as a cold state system. And what this means is that there is state. You have state, right? You have the state of your order. You have the state of your IoT device. So in a stateless system, what happens is a request comes in to change, say, the state of a given entity, your order or state of a given IoT device. You have to retrieve that state, cold state from storage, bring it into memory, make your changes, and then persist those changes back down to the database. So you're taking your hot state and then pushing it back down to cold state, and then you throw your hot state away. So the reason for that is it reduces a lot of complexity in distributed systems, but again, it kind of comes at a cost, because you're always having to retrieve your state, change it, make it hot temporarily, push it back down to persistence, and throw it away. With the way we do it in Akka is that the state stays in memory as long as possible, and only stays in memory when it's in active use. When it's not in active use, the state it's called passivated. It's pushed out of memory because there's no point in keeping it in memory if nothing's using it. So I tend to like to not think about things as stateless or stateful, but hot state versus cold state, as I just explained. I think it's kind of an interesting way to look at how things are evolving in the way we build our systems. So back in this demo application, with the two services, the simulator service just uses the journal. It just has a write side. I'm not really doing any big queries against this service, so I don't need a read side. I just need a simple write side. And I want this thing to run very fast. The twin service, this is really set up to be like it's a service that's sitting there receiving telemetry messages from real devices out in the physical world. And the idea is that these messages are coming in, and they're commands that are coming in. Telemetry messages are interpreted as commands coming into the twin service, and those commands are coming in, and they're getting persisted as events in the journal. But then there is a view. We also call it a projection. It's called Akka projection. But in any case, it's a view. And what's happening here is that the view is structured in such a way that is used in the user interface. So, and it's giving me kind of a view of the state of devices that are distributed across the map. And the processing of the view is kind of non-trivial in this demo application. There's some interesting things going on here. So there's that eventual consistency delay that's going on between the journal, the events getting initially persisted there. That's a transaction, it's done, everything's finished. And then there's a process that's running here. It's called an event handler. And an event handler is just pulling those events from the journal, new events from the journal as quickly as possible, and then invoking processes that are updating my view data, which is in this case, the journal is a Cassandra, a set of Cassandra tables. My view is a simple relational table. So I'm updating rows in the relational table as events are coming in. Like create a device, create an IoT device, create another IoT device. And what I'm doing is I'm capturing that data in a queryable form that's optimized for the kinds of queries that this application has to do. So to kind of show things, now that you kind of have an idea of the mechanics of what's going on in these services, I want to go back to the demo app, and let's take a look at things again. So when I did an operation, what you saw was there was a delay that occurred before we actually saw things on the map. So what's happening here is that when I click and send in a request like create some devices, for example, that request goes into the SIM service. It's a single HTTP request goes into the SIM service. The SIM service takes that and decomposes it down rather quickly through a kind of an interesting hierarchy of Akka actors to, like when I created 1,024 devices, it ended up creating 1,024 actors in the simulator side. And those actors then, each one was emitting telemetry messages to via gRPC to the twin service. So a whole bunch of messages went across to the twin service. Now, of course, both these services are running in Akka clusters. So they're running in Kubernetes. So if you're familiar with Kubernetes, each node in the cluster is a different pod running in a Kubernetes pod. So I've got like 6 pods running for the SIM service and 6 pods running for the twin service. So I triggered a bunch of activity, and all 6 of those simulator JVMs lit up. They processed like 1/6 of the activity, and they were firing off gRPC messages to the twin service. And there was 6 nodes of the twin service, and they each can receive gRPC messages, and each one of them are receiving their messages and processing them. So I'm going to do it again. I'm going to zoom in a little bit, and I'll perform another operation. I'll do a create. I've got the rate set to 500. So when I click and do a create, what's happening then is that it's sending that request to the SIM service. The SIM service did a bunch of work, and then sending over 1,024 messages to the twin service. Twin service gets it. Those event rows are created, and then that information then is digested into the view. So the data that we're seeing in the map here is coming from the view. So that the request went through the full gauntlet of, it's like over the course of 2 seconds, 1,024 users hit buy, if this were a retail type of an application. These backend microservices had to handle these requests, quickly, and so we saw that. So it ran pretty quickly, where we saw the 1,024 devices get created. And I can I'm going to increase the rate a little bit. I'll go to 1,000. My Amazon account that I'm using is kind of limited, and because the way the databases work is that I can set things up to go to a different rate. But I'll go out just for fun and try and create 4,000 devices over the course of 4 seconds, and I'll wrap up the talk. But I'll zoom in as it's happening. So if everything works well, we should see the 4,000 devices get created. Wow, that ran pretty quick. So now you can see each of these regions. I zoomed in a little bit. They're all 256. If I zoom out, 1,024, 1,024, 1,024. Zoom out, 4096. So pretty fast, not super fast, not a mega service, but a kilo service for sure. Because there's a fair amount of activity that's going on behind the scenes to make this work. And I think you have a little bit more insight now about how this works. So it's kind of an interesting application. So I just want to kind of wrap up with, how fast is fast enough? And I've been asking around. One of the advantages of working for a company like Lightbend is we work with a lot of different companies, big ones, many of them, and a lot of them are building big systems. So I just started looking around, but I came across an article recently that said something like, this year, Amazon has been averaging around $10,000 US dollars per second in orders. And I just did a little bit of math, and I said, all right, let's assume that each order is around $50. And that means that every second they're doing around 200 orders per second. Okay. So those are logical operations. Now, of course, to build up an order, there was a series of logical operations that had to occur. So say like for every order, there were maybe 5, 10 logical operations. So we can say it's 1,000 or 2,000 logical operations per second. This gives a sense of the scale of, like the mega retail site of the world, right? Amazon. A little bit more theoretical, but I just did a little bit of math, and I said, assume that we have a system that's handling 1 million IoT devices, and that those IoT devices are constantly sending telemetry messages just to say, I'm here, I'm alive, and maybe to communicate some kind of a state change. But they're sending messages about once a minute. So that means that the back-end system has to handle around 1,700 messages per second. Well, I'm sorry, I did the math, right? And I'm assuming that every 10 minutes that one of the messages had a state change. Like say it's a temperature gauge and the temperature went up or down in every 10 minutes or so. This is kind of high, but I wanted to kind of push it. But even at this rate, with 1 million devices sending messages once a minute, and every 10 minutes something interesting happens to the device that the system wants to actually record in a database, making that assumption, we're looking at only around 1,700 state change operations per second. So it's well within a low kiloservice range. But I think even though this decade is getting off to a rough start, I'm kind of excited for in our business for what's going to be happening over the next this decade. Like what's going to be, where are we going to be at in 2025? Where are we going to be at in 2030? Which isn't too far away. I think our systems are going to constantly be challenged to handle ever higher loads, and we have to be able to build those kinds of applications. I think things like distributed systems, hot state systems, CQRS, and so on are some of the real techniques for how you can build these types of higher end systems. And I just think things are just going to get more and more interesting. So these pictures, kind of shows how fast can you go from walking to riding horses to driving cars, flying in airplanes, rockets, and then way off in the future, some kind of hyperdrive type of space starcraft or something like that. But who knows? The future is always a surprise, I think. So these two projects, the services, I have 2 GitHub projects for them, GitHub repos. So here's the URLs for them. It's under my name, my username, McKeeH3. So we're an Earth Sim and we're an Earth Twin. There is a README, and this is still a work in progress, but I've got I think a reasonably complete README for taking these things, if you're interested, cloning them, building them, and deploying them to Minikube or Minishift or something like that. Something local running on your your own laptop, your own development system. I've tested it this way, but I've also been testing in Amazon and Google and things like that because I wanted to have a more, a real production-like environment to do some testing. So I'd love it if you guys were to grab this, and I'd love to hear from people that have played around with it and maybe saw a problem with it or made some changes to it, or just whatever. I think it's been a fun app to play with. So that's my talk. I hope you enjoyed it and got something out of it, and I think we'll be going into a Q&A.